Hello and welcome to this first video all about transformers, the key model behind almost all of the generative AI that we know and love. So ChatGPT, Claude, Gemini, and so on. Over the next few videos, we are going to take a look at where this idea of the transformer came from, what the key parts of the transformer architecture are, and how those steps work in both training and at inference time. In other words, when we are looking to make a prediction. Now, while transformers have and are used with audio data and image or video data, we will simply focus on language data for our examples here. And on screen, this is essentially what a trained language model is looking to do. It's going to take in some input text, and then it's going to predict the most likely next word, and then the most likely next word after that, and so on. So let's start our journey here. And you will no doubt recognize these terms and these images from the course. These are the two types of neural network architectures that we learned about and applied. So the artificial neural network, which we used to predict on some tabular data, and then the convolutional neural network, which we found was great for image data. And why are these important? Well, because a transformer is nothing but another type of neural network. And so let's just linger on these two models for a second and discuss at a high level what they did. They took in input data like pixel values or numeric features, they passed this information through layers with weights and activation functions, and as they did this, they essentially created abstract features or abstract ways to represent the data, all of which helped them make their final predictions. And a transformer is very similar in this context. If you remember our image search engine project, where we passed many shoe images through a pre-trained network, VGG16 in this case, and thus we created vectors that stored abstract numeric representations of all the different shoes and their features. With these vectors, we could then pass in a new shoe, create those same vectors, compare them to the ones that we had stored, and output the best matches. And this is a key thing to think about when we learn about transformers with text data. If we can represent text using numbers and specifically vectors across a high number of dimensions, we can get a really good understanding of meaning and context. And this is exactly what enables these transformers to do the incredible things that they do. Now, before we start looking at the architecture of a transformer in more detail, I want to quickly mention its precursor, the RNN, or the recurrent neural network. Now, prior to the transformer, this was the deep learning approach that you might use for sequential data, and that is exactly what text is. It is sequential. Now, an RNN, when focused on a text-based task, such as predicting the next word, would essentially process one word at a time, left to right, and try to keep track of what it had seen so far. And this all sounds sensible enough, but there were a couple of key problems. These models didn't really understand context, and they had quite a short memory. If we had, as you can see on screen, I went to the museum where I saw a painting by Picasso, it was blank. By the time the model gets to it was, it would sometimes have completely forgotten that we were talking about a painting or that we were specifically at a museum. All things that would provide context for the most likely next word. You could almost think of an RNN like your phone's autocomplete. After the text, hello, how are, it may well suggest you. But, and I'm sure you've tried this yourself, if you keep accepting its suggestions, the sentence starts to make no sense. It sees only the last few words, not the full picture or the deeper context. And these issues are exactly what brought around the transformer, as it has functionality within it that precisely addresses these pitfalls. And this all came to the fore in 2017 with the release of the paper, Attention is All You Need, where they proposed the new architecture known as the transformer, and that you can see to the right of screen. And the reason that the paper is called what it is because of this new mechanism called self-attention, and we'll talk about that more in one of the upcoming tutorials. Now, at first glance, that architecture on the right there looks pretty intimidating, but what we are going to do is simplify it down to the key aspects that you really need to know. So instead of what you see there, which is the original encoder-decoder setup from the 2017 paper, we are going to instead be working with this here, which is more akin to how the GPT model that drives ChatGPT actually works. And to really focus in on the task at hand, before we get into the weeds, you can see that down the bottom there, we have some input text going into the model. So let's just say that this input text was, the cat ate the mouse because it was blank. And so at this point, we're thinking that this transformer model, which remember is just a type of neural network, we're thinking that this has already been trained. So it's already processed a ton of training data and it's learned as much as it can about the meanings and context of words and text. And we'll talk more about how that training process happens at the end of this section, but for now, this model that we're discussing here, let's just think that it is ready to go. And so in this case, our input text would be passed through the architecture of the transformer, and at the end of all of that, the model will make its best prediction for the next token or word in the sequence. And so as a human sitting there, what do you think that next word could be? I guess it could be a number of things. A cat might eat a mouse because it's naughty. And that could very well be a fitting word here, but what is interesting is that this word, naughty, in this sentence is referring to the cat. But what if the model decided that the most likely next token was instead tasty? I think this is just as plausible in this sentence, but this time, tasty, this instead refers to the mouse, not the cat. And this idea is important, and it's why the transformer models are so powerful and why they're so much better than their predecessor, the RNN. They are looking for clues in the full context, so word ordering, links between words and their meanings, tone and intent, to figure out what truly is the most likely next word or token. And all of that learning takes place in those middle orange boxes on the left, in that area called the transformer block, and we will discuss that and how it works in a moment. But sticking to what we are talking about on screen here, I actually went through and ran this through the latest version of ChatGPT, and it concluded that the most likely next word was actually hungry. And what this means is that it's looking at this context and it believes that based on everything that it's learned in training, the word it in our sentence here most likely refers to the cat. And with that in mind, it also believes that the most likely descriptor for the cat in the sentence to be eating the mouse is because it is hungry. So all I wanted to do here was reaffirm exactly what the goal is for a trained LLM, so a text-focused transformer model. It is looking to take in a sequence of text, understand everything it can about the context in terms of the ordering of words and the linkages and relationships between them, and provide its prediction for the next word or token. And this is really at a high level what products like ChatGPT are doing behind the scenes. So with all of that in mind, let's take a deeper dive into each of the steps from bottom to top in our architecture. And let's start right at the bottom with our input text, how it's processed and how it moves on to the next parts of the architecture. And this is exactly what we will discuss in the next tutorial. I will see you there.